an online class for Friday of this week, but we'll actually do it for Wednesday as well. So this will be our only face-to-face class meeting this week, and then I'll put a lecture video online for Wednesday and Friday. And I'll email you that, and I'll put the link also on Blackboard. So looking at the schedule, here we are. This is class 15. Today we're going to be talking about pumps, and we'll also be going through some pumps topics on Wednesday and Friday. And then a week from today, I'm going to assign the design project. And I'll probably post the PDFs of that on Blackboard before Monday's class if you want to take an early look. There's no need to. I know you're busy with lots of things, and so just only if you're curious, you can look that up in advance. And I'll bring printed copies of all the materials I want you to have for that class next Monday. And you should also have water gems installed for next Monday. We're going to work an in-class example where if you don't have water gems operational next Monday, then you're really going to miss out. So you can sit and watch, but it's not necessarily the same as actually having the program running on your computer. So you really need to, if you haven't already, finalize the installation of water gems so you're in a position to participate in Monday's class next week. And then Wednesday of next week, we're going to have our first midterm exam. And I'll provide the formula sheet for that. There's nothing that you need to bring to that exam aside from a pencil, calculator, and lots of knowledge. So I'll put the formula sheet on Blackboard early so that you can just get familiarized with what that looks like and where the formulas are and so on. So anybody have questions related to scheduling or anything else before we move on? For the exam. Yes. Yeah, you'll need your computer. Yep. So we've done a couple of different problem-solving things. You'll need Excel for the exam. Yeah.
And you said you're providing a formula sheet, we're not making one?
That's right. Yep. Other questions? All right. Well, so looking more at the near term, this homework 5 that you're working on right now, which includes a Hardy cross problem with 3 loops, and a water problem, water hammer, and surge tanks, that's due on Wednesday. And I've gotten a couple of people asking questions about the Hardy cross spreadsheet, so that's good. It gives me a sign that people are making progress. And then we'll have the online classes Wednesday and Friday. So we're moving to chapter 9 now in the textbook. I will encourage you to follow along there. You know, there are a few additional problems that are examples, and a different explanation perspective I think can be valuable to help solidify everything in your mind. Any questions before we start talking about pumps? All right. Pumps add energy. And water flows through a network because there's more energy upstream than there is downstream. And sometimes there isn't enough energy to overcome pipe friction. Sometimes there's not enough existing energy upstream to overcome an elevation difference. So if we want to get water from one point to another, often gravity flow isn't going to be enough. And so we have to add additional energy to get water moving as quickly as we want or to overcome resistance, whether it's an elevation change or frictional resistance or whatever. So the simplest kind of a pump is a positive displacement pump. And what a positive displacement pump is, it's a pump where with each rotation or with each cycle of the pump, a fixed volume of water is delivered from one point to the other. So it delivers a fixed quantity, and it's not necessarily even adding pressure. It's just moving the water from one place to another. Typically, positive displacement pumps that are open to the atmosphere like this don't add any pressure at all and are just lifting the water from a lower elevation to a higher elevation. So it could be from a stream into a food processing plant or a mill. And here's a side view of a positive displacement pump. You can see that this looks like a screw in a sleeve. And the purpose of the sleeve is to provide the barrier or the channel that allows each rotation of the screw to lift the water a little bit higher. So it could be a person cranking a handle, it could be a motor, that's on there causing it to spin. But this positive displacement pump, once the water exits the pump, it has no increase in pressure, but we've lifted the water from its original water surface elevation to some higher location. So here's our energy equation. And remember that pumps add energy, and there's three different forms of energy. There's pressure head, elevation head, and velocity head. And the pump types that we're going to talk about today either add elevation or they add pressure. But there aren't pumps, so far as I'm aware, that only add velocity. You know, a pump can increase the velocity that water flows through a system, but the pump itself, from the inlet to the outlet, typically wouldn't increase velocity in the exclusion of the other two factors. So just keep in the back of your mind that pumps are adding energy, and how is it that they're adding energy? Here, the simplest positive displacement pump is just increasing Z from location 1 to location 2. So here I've indicated a couple of locations, 1 being the origin, 2 being the outlet. Both of them, it's water at atmospheric pressure at 1 and 2, but location 2 has more Z. It's the downstream location. Okay, these are all examples of other positive displacement pumps that, like screw pumps, have with each cycle a certain volume of water that's being delivered. So starting with the rope pump, try and visualize in your mind what we have is a rope and rubber plugs that are affixed to the rope at specific intervals, and the rope dangles down into a reservoir, and it could be a groundwater reservoir, it could be water at a lower water surface elevation like in a lake or a creek. But with each crank of this handle, which is connected to the rope, it's drawing the plug up through a pipe. And so the plug, the rubber plug, has a diameter that's just barely smaller than this confining pipe that's also down into the water. And so the plug is sealed, it's lifted up, and the water is perched on top of the plug, and then there's this outlet pipe that you can see that the water is being discharged out to a bucket. So a rope pump, positive displacement, each cycle is drawing a certain volume upward. An internal gear pump is a similar thing, where you can see the rotating gear is a solid, that the water can't flow through the gear, but there are these voids that, because of the shape of the gear and its location, these voids have space that the fluid can fill, and so it's drawn into the gears, it's discharged from the gears, and each one of these pumps do a similar thing. With each rotation, it's pushing the water, a certain volume of that, from the inlet to the outlet. And so these positive displacement pumps are not used in large volume networks. You wouldn't see this delivering water for like a city. A peristaltic pump is something that you'd see in a lab, like in a wet lab where they're doing maybe chemistry analysis or environmental sampling. It's common to see a peristaltic pump. What it is it's a flexible tubing. And so you'd have like a plastic tube that's threaded through this circular conduit, and so then a roller is pressing the tube together, it's squeezing the tube, and it's forcing the water out through the discharge area. And a peristaltic pump is beneficial because you can have really direct control over the flow rate, and it's good for really slow flow rates. Like if you wanted to deliver 1 milliliter per minute, a peristaltic pump could be dialed back really slowly. You could have this turning at just a glacial pace, and so it would be a way of having a very minute quantity of water, maybe with some chemical dissolved in it, delivered to have a chemical reaction. So these are pretty rare, obscure pump types that you won't often see except in very specific applications where you want to have a direct control over how much flow there is. Centrifugal pumps, by contrast, are very widespread. And they're widespread because for the high flow rates that we need to have delivered to homes and businesses, they're very efficient. They can deliver a lot of water at a pretty high efficiency. And the way that these work is by increasing the pressure. It accelerates the fluid due to a curved vane structure. And water would enter the suction side of a pump, and its direction is changed as it's accelerated. There's this metal plate, an impeller plate, that spins, and as it's spinning, it increases the pressure on the discharge side. And let's watch a video that explains a little bit about different sizes of impellers and just some of the considerations that come into play when you're using a radial flow centrifugal pump. Typically, but it talks about how what's happening is through acceleration, the velocity of the incoming water increases due to the shape of the vanes, and then the velocity is exchanged into an increase in pressure through the volute. And the other common type of radial flow pump is if you have the impeller submerged in the pipe itself rather than in a separate pump casing. Axial flow pumps like this could be common when you're trying to lift groundwater. And so they could have the motor at the surface where it's able to be cooled and accessed if it needs maintenance, but then a shaft could be down in fact, I should rotate this just to make it more clear that a common application would be if you're trying to lift the water from below, then you'd have at the surface a motor which is spinning, and then it's lifting the water through the pipe, and then it's going into the network from there. So an axial flow pump is doing a similar thing. It's just increasing the pressure, and if you look at the velocity of the fluid before the impeller and after the impeller, the velocity of the fluid is the same. Because think about, you've got a constant diameter pipe that this impeller is situated inside of. And we know that flow in has to equal flow out. That's the continuity principle, is Q in equals Q out. As long as the diameter is the same, what that means is that the velocity in and the velocity out will be the same. So the velocity through a pipe isn't the same before and after a pump is turned on. That's not what the continuity principle says. But what the continuity principle says is that during steady, uniform flow, that the flow in and the flow out are equal. And so for a constant diameter pipe like this, what's being increased from the inlet to the outlet side is pressure. It's not increasing the velocity. It's not necessarily changing the Z value, as this next diagram illustrates. So I'm making the same point here in this cutaway, where water is being lifted from with a centrifugal pump from a water reservoir, and it's flowing, let's say, towards an industrial area or consumers of water. So if we consider two locations, one that's upstream and one that's downstream, you can see that this is on the same horizontal plane. So the elevations are the same, and the diameters of the pipe from the inlet side to the outlet side are the same. So the velocities aren't going to be any different when the pump is on and operating. But what's happening is that the system is having additional pressure added to it. And so if we were going to draw a sketch of the energy grade line here, so we've got this pipe that's drawing the water up due to a pump, and the water's going out. So if we did a sketch of the energy grade line, the energy grade line starts at the water surface. And so it would be going down, and then there's a sudden increase. And then the energy grade line is going down again because of the energy loss due to pipe friction. So EGL takes into account the velocity head plus the pressure head plus the elevation head. So from here to here, the elevation's the same, the velocity's the same. So what form is that pump adding energy? It's just a sudden increase in the pressure. And so at location 1, the pressure maybe would be 200 kPa, and at location 2, it could be 600 kPa. It's an instantaneous increase in pressure. So we have just a straight line up from the EGL in a case like that. And so it's added as a pressure increase. And when we have the energy equation, we've sometimes abbreviated the energy equation like it's shown on the screen here. But let me go and find the full form of the energy equation where the pump head term is included there. Because, you know, we don't always have pumps in every application of the energy equation, but when we do, the energy being added is, it's on the left-hand side of the equation. Here we go. Let me copy this onto the slide. And we'll just compare that it's added with the energy at location 1. All right. So here's the full version of the energy equation. And so the important thing to keep in mind is that if you are looking at which side of the formula to add it, it is on the left-hand side of the equation. So if we're saying here at location 1, the amount of energy at 1 plus the energy added by the pump is equal to the energy at 2. If these two are really close together, there wouldn't be frictional losses between them. If we were saying now location 2 is some distance downstream, so if this is location 2, the energy at 1 plus the energy added by the pump minus the losses is equal to the energy at 2. So always keep the directionality of the energy equation in mind, that 1 is upstream, 2 is downstream. Any questions so far about pumps or the energy equation? All right. Now, as the video that we just watched mentioned, what it's doing is it's turning electrical energy into fluid energy. And it's not even that simple. It's turning electrical energy into mechanical energy. That's what the motor is doing. And so the motor is connected to the pump, and the pump is turning mechanical energy into fluid energy. So the pump equation, the pump equation converts the pump head that's added to the amount of power that's being added to the system. And so I think you may have seen this in fluid mechanics, where the flow rate multiplied by the unit weight multiplied by the pump head will tell you how many watts are being added to the system. So P has units of watts, Q would have units of cubic meters per second, gamma is newtons per cubic meter, and pump head has units of meters. And so if you add that all together, you're finding out here in the SI version of the equation how many watts the pump is adding to the system. In BG units, remember 550 is the conversion between foot-pounds per second and horsepower. So you'd find out the horsepower that's being added to the system by taking into account cubic feet per second, unit weight is pounds per cubic foot, and pump head would be units of feet. And then this conversion factor to get horsepower. But the amount of energy that actually gets into the system is reduced by efficiency factors, because motors aren't 100% efficient at converting electrical energy into mechanical energy, and also pumps aren't at 100% efficiency in converting mechanical energy into fluid energy. So we have to take the efficiency into account. The overall efficiency is the product of the motor efficiency and the pump efficiency. So sometimes those efficiency factors would be given to you in the problem statement, or you may have to look them up off of a figure and find out what percent efficient is the motor and the pump. And then the actual power that's added to the system would be the input power, like the electrical power that the combined motor pump network is using, the electrical input power divided by the efficiency. And we'll work an example just to show you how that fits together. But pumps don't always act at the same efficiency factor. Like their efficiency may be high at a certain flow rate and adding a certain amount of pump head, and then much lower at different flow rates. The design of them, some pumps are designed to have really high flow rates, some pumps are designed for lower flow rates, some pumps are intended to add just a little bit of pump head, others add a high pressure but at a lower flow rate. So there are curves that help us to understand the efficiency and the intended design of any particular pump. And so picking the right pump for the application where it's going to be used is a pretty important task. And the efficiency depends on what speed the pump is being rotated at, the flow rate of the intended application, fluid properties, which depend on temperature. Remember that density and viscosity are variable based on the temperature. And then the excess energy that's lost by a pump is typically most of it lost to heat. So it's the electrical motors are warming up and that heat is just being dissipated as waste. There's friction, so there's a little bit of the materials that are getting worn out, and pumps have a little bit of pressure leakage sometimes where energy could be lost that way as well. The way that a pump is characterized is with a pump performance curve. And so the shape here, this is the typical shape of a pump performance curve. And what it shows is that you could add a lot of head at a low flow rate, and the head that's being added is, you can think of that as the pressure. You know, head is actually the pressure divided by the unit weight, but it's how much energy is being added by the pump. And so at a low flow rate, the pump adds a lot of energy, but as the flow rate increases, there's a decreasing rate of pressure that's being added. And this formula, this H sub P equals 24.4, like it's not every pump has these coefficients and intercept. This is just an illustration to show you the two components here. So first of all, the 24.4, that's what we'd call the shutoff head. And so that is how much head the pump is adding to the system at essentially zero flow rate, or at a very, very low flow rate. But then as the flow rate increases, there's a certain factor. Here it's 7.65. There's a coefficient that allows us to calculate with each unit increase in flow rate how much the shutoff head is declining. And you'll notice it's squared. It's Q squared. And so there will be some curve, and we can get that from the manufacturer of the pump, what the equation or the curve looks like. And what we'll have to do is we'll have to look at where the pump is going to be used. So look at the pipes that it's going to be connected to, look at where the water is being drawn from, where it's being discharged to, and we would prepare what's called a system curve. And so here you can see a pump in the context of where it's going to be used. It's pumping water from a lower reservoir up to a higher reservoir. And so we would prepare, using the energy equation, an equation that relates how much pump head is required for a certain flow rate. So we'd say, you know, like what is the elevation at 1? What is the elevation at 2? How much losses are there through the pipe network, both the local losses and the friction losses? And you rearrange the energy equation to solve in terms of H sub P, and then you put the two together. You put this system curve, you overlay it on top of the pump curve, and then you'd find where do those two curves overlap. And that's the operating point. So rearranging the energy equation in terms of H sub P, the pump curve is in terms of h sub p. And you just solve for what is the Q value that makes the two h sub p's equal. And so here it's showing the operating point. We have the typical shape of the pump curve, which is downward as you move to the right. The increasing system curve just says that as the flow rate increases, the head losses are going to be going up. And so that's why the curve is increasing for a system curve, is that with each increase in flow rate, there's more and more friction losses. Remember that whether we're talking about Darcy-Weisbach or Hazen-Williams, the head loss is always to flow rate to some exponential factor. So, in the case of Darcy-Weisbach equation, h sub f is FLQ squared divided by D2GA squared. So as the flow rate increases, the head loss is going to increase to the square of the flow rate. And so that's why this is getting steeper and steeper. And so the operating point is setting the two terms equal to each other. All right, let's watch this other video where it'll talk about the operating point. All right, so let's go through the process of calculating the operating point for a system that's described here. Let's say that we have water that's going to flow through a length of 120 meters, and the diameter of the pipe is 250 millimeters, and we know the equivalent sand roughness, and there are K values there because of local losses, fittings, bends, and so on. And then the elevation change from the inlet to the outlet is 9.1 meters. Now the system curve, this is just the energy equation. We've seen this before where we've just rearranged the energy equation, but we're writing it in terms of flow rate, Q, instead of in terms of velocity. And then also we've isolated h sub p. So ordinarily that would be on the left-hand side of the equation. We've moved everything else over to the right-hand side of the equation. And then we have a pump that has these manufacturer-provided characteristics, and we want to know what flow rate is going to occur when we put this pump into this system. Now, how quickly can it circulate water? Now, the tricky thing is that we don't know the F value until we know the flow rate. And so, as it says on the screen there, the suggestion is to begin with the fully turbulent flow assumption to calculate F. So remember that in the fully turbulent flow assumption, we just assume that the Reynolds number is very high because we have a high velocity, and then that makes the F value simpler to calculate. And then anytime we use the fully turbulent flow assumption, we'll have to go back and check to see if it's valid. All right, so let me pause for a second. And what you should do is, first of all, calculate the F value, and then substitute all of the given details to find out what is the system curve, and then equal the system curve to the pump curve. So you'll have HP in terms of all of this, and then you'll have this H sub P. Set the two equations equal and solve for Q. Okay, so for this example, we go through the initial steps of calculating the cross-sectional area of the pipe and the F value using the fully turbulent flow assumption. And then we substitute that into the energy equation in terms of H sub P. So you see, I went through all of those steps, and the system curve is 9.1 plus 249.74 Q squared. So that says that our cutoff head is 9.1 meters, and then this 249 just indicates how much the pump head is reduced for each incremental increase in the flow rate. So the problem-solving strategy is set the system curve equal to the pump curve. So the system curve is what we've just calculated. The pump curve was given in the problem statement, and we're solving for Q. So it is 9.1 plus 249 Q squared equals 24.4 minus 7.65 Q squared. So I just move Q to the left-hand side of the equation, all of the numbers to the right-hand side of the equation, and solving for Q, the operating point will be 0.244 cubic meters per second. And just to check the fully turbulent flow assumption, the velocity of the flow with this flow rate is 4.7 meters per second. And so if I went to a Moody diagram and checked what would the F value be, it turns out that the F value is unchanged, that the velocity here is high enough that actually the fully turbulent flow assumption is valid. Now we can solve it on paper numerically. The other way to handle things is here I've sketched out the pump curve just using the formula that was given. So this 24.4 minus 7.65 Q squared was given in the problem statement. And then I did the system curve for a variety of different flow rates. And then I graphed the two. And so what I'm looking for is what is the flow rate that makes the pump curve value and the system curve value the same. So I did the difference between the two, and it turns out that it's that same 0.244 flow rate that makes the pump curve and the system curve equal. So it's the operating point where the two lines intersect. All right, we are out of time for today. So remember, the rest of this week, Wednesday and Friday's class will be a lecture video that's online. I'll email you the links. I'll also post it on Blackboard. And then if you've got questions on your homework between now and Wednesday when it's due, stop by my office, send me an email, whatever I can do to help, let me know.